I'm Amy, and I'll be giving a talk about our paper, which tries to recover hardware corruption errors with distributed redundancy. So the main motivation for our work is the fact that Flash is getting denser, and as a direct result of this, Flash has shorter lifetimes. So as a demonstration of this, here's a graph that shows error rate versus age for a variety of generations of Flash. So to determine the lifetime of each generation, what you typically do is superimpose some constant acceptable error rate, and then the lifetime of each generation is determined by where each of these curves intersects this constant line. So for example, TLC, being the densest generation of Flash, has the shortest lifetime, and SLC has the highest. Shorter lifetimes, however, are a problem for a number of reasons. So first, shorter lifetimes means that data center operators need to closely monitor Flash writes. This could mean that data center operators are, for example, throttling applications that are going over their daily allotted write IOPS. Also, the memory to Flash cost ratio is increasing, which means that a lot of operators are also migrating workloads from DRAM to Flash, and this will only further increase the pressure on Flash. And finally, because of these trends, data center operators actually can't adopt newer generations of Flash, such as QLC, because they have such short lifetimes that they can only be used really for read-only workloads. And at that point, why are you using a QLC device? So what we're trying to do in this work is try to figure out how we can increase Flash lifetimes. And the key observation that we make is by simply increasing this constant acceptable error rate, we can increase the lifetime of Flash devices. So for example, if we look at TLC, we've now just greatly increased TLC lifetime simply by moving up this constant line. But doing so is easier said than done because hardware is expected to have low error rates, and software has been designed around this assumption for a long time. And so this causes two problems. One, which is a correctness problem, because by increasing the error rates coming off of the device, you could actually just fail the software. And this is also a performance problem, because if the software does have some sort of way of handling these errors, typically this error handling path is not performant because it's assumed to be a rare event. And so if we're going to live in a world in which Flash devices are exhibiting higher error rates, we impose two new requirements on software. Again, there's a correctness requirement. Software can't fail, and it needs to continue to function even if it encounters these errors. And second, we still need to be performant despite having to run this error handling code, I guess, more often than usual. And so what we come up with in our work is a set of principal techniques called direct, or distributed error isolation and recovery techniques, which allow developers to retrofit their storage applications to live in a world in which Flash has higher error rates. Direct is basically based on two main intuitions. So the first intuition is the observation that there's enough redundancy at the distributed application layer due to replication that we can actually correct these hardware bit errors without adding additional redundancy in the storage stack. So for example, you can make the argument, why don't we just put another layer of RAID inside these devices, or across these devices? And the game that we're trying to play here is that use the existing redundancy, which is already enough in the storage stack, to correct these bit errors. And the second intuition is that we observe that we need to optimize error recovery performance, and I'll get into this later. And so as a recap, if we're able to do this, this means that Flash devices can expose higher error rates, which means Flash devices can have longer lifetimes. And this results in direct cost savings. Okay, so let's look at what bit errors would do to the storage stack. This is a simplified example of the storage stack that we're looking at. So at the bottom, if you have unreliable Flash, this error could actually propagate to any of the layers in the storage stack. But in this work, we assume that we have some hardened file system that we can use. We didn't focus on the file system in this work because there's actually a lot of ongoing academic work and industrial work, and even papers published at this year's ATC about how to harden file systems against hardware corruption errors. So we focus on the local data store, also because the majority of data center data is stored in these local data stores. So you get an economy of scale argument here, because if you can actually make local data stores tolerant to hardware errors, then you can actually run a lot of Flash devices beyond their given lifetime. Okay, so if we zoom into this local data store, the errors occur in basically two flavors. They either occur in metadata, which we obviously have to fix, because in most storage applications, if your metadata is corrupted, this basically means the application is not going to start up. So this is pretty straightforward. This is the first technique. We observe that we need to protect and fix errors in metadata, and we do this pretty simply. We just locally replicate metadata, and this is the straightforward technique that's been found in a lot of previous works as well. The second flavor is corruptions in data objects. So this is the meat of the direct techniques. So we observe that we have to fix these errors, but here's a strawman approach of doing so. So suppose that we have a data object that's corrupted. Then the simplest observation we make is, oh, well, we've replicated this entire node, so let's just copy this entire node over, similar to what you would do during a node failure. This is obviously prohibitively slow and obviously unnecessary if you've only gotten a corruption on a single data object. So really the question here is, how can we isolate the data necessary for recovery? So this is the meat of the second technique. What we observe is that we need to minimize the granularity of data recovery for corrupted objects. And by doing so, you can minimize the amount of time that's spent in recovery. And we observe that this is particularly challenging in logically replicated systems. And again, I'll go into this when we have a concrete example. And finally, the third technique is that we observe that we need to provide safe recovery for these recovery operations. Again, here's a naive recovery protocol that explains why we need to do safe recovery. So suppose we have a data object that's corrupted, and it has some number of replicas. And let's say we want to do a recovery of A that's corrupted. So we send a request to one of its replicas, and we say, hey, give me the uncorrupted version of A. Then there's some concurrent write operation that comes in that writes A to A prime. And this gets replicated asynchronously to all of its replicas. So let's say it gets replicated first to the corrupted replica, which gets updated to A prime. Then this recovery request comes back and says, oh, here's A. So it gets updated back to A, and then the write operation finishes by updating the middle replica to A prime. And so you can see at the end of this that there's an inconsistent state in the system. So the third technique is basically observing that we need to do safe recovery, and really in a lot of distributed storage applications, this simply means running recovery through whatever distributed consistency protocol that the storage application already has in place. So in the paper, we present two implementations of direct, HDFS and ZippyDB, to show that it's generally applicable to a broad variety of storage applications. But in this presentation, I only have time to go through the ZippyDB implementation. So if you want more details, please refer to the paper. So ZippyDB is a distributed key value store in use at Facebook, and it's backed by RocksDB. So here's a quick overview. So each instance in Zippy has a primary and a number of secondaries, and each of these, again, are backed by RocksDB, which is the local data store. Writes come into the Paxos log. Zippy is basically a shim layer of a Paxos log on top of Rocks. So write requests come into the primary, this gets replicated to the secondaries, and then eventually each of the individual replicas will pull these write requests off the log and update their own state. So this is pretty straightforward SMR. So in the verbiage of earlier, the Paxos layer is the coordination layer, and the RocksDB layer is the local data store. So what we're trying to do in this work is trying to fix corruption errors that might occur in RocksDB. So as a brief overview, this is how ZippyDB handles any kind of corruption that might exist in Rocks. For object reads, Zippy just cancels the read and tries to retry at another replica. But in Rocks, there are also a large number of background reads due to the background compaction operation. And Zippy actually handles this very poorly. They will actually crash an entire ZippyDB server when a single RocksDB instance encounters a compaction error. And each ZippyDB server can actually hold like hundreds of Rocks instances, so this is pretty bad. So what we do in direct is we try to fix these compaction errors without killing an entire node. So as a recap, these are the three techniques, and let's see how we apply them to ZippyDB. First, we need to replicate the metadata. So here's the file layout for SS tables in RocksDB. You basically have a number of data blocks, which are followed by metadata blocks. So really simply, this is very straightforward. We just replicate the metadata blocks in line. RocksDB also has a number of metadata files that we also replicate, like manifest and the log file, and those are replicated separately. OK. So now how do we fix errors in the data objects? This is difficult in RocksDB, which is a logically, or ZippyDB, which is a logically replicated system, because if you find a data block that's corrupted, you can't find an exact copy of that data block anywhere else in another replica. And this is because each of the RocksDB instances are applying writes at a different rate. They might be doing compaction at a different rate based on different pressures from their local system. And so you're not going to find that exact physical data block anywhere else. And so what you have to do is figure out which key value pairs you actually need to recover. And there's no way of doing that because your data block is corrupted. So instead what we do is we use the index block entries in the SST file to get a key range that we need to recover. And so this index block will tell us that, for example, we need to recover all keys in some key range, key 1 to key 2, in order to fix this corrupted data block. And so even though a key range is a higher granularity than trying to recover just a single key value pair, this is a much smaller granularity than recovering an entire data node, which is what ZippyDB does now. And finally, to do the last technique, to do safe recovery, we basically run recovery through the Paxos log in ZippyDB. So we basically treat recovery operations as a new special type of request that you can make in the ZippyDB log. So here's an end-to-end demonstration of the recovery protocol. So a Rocks instance will basically try to do compaction, and in doing so, discover that it has a corrupted data block. Rocks will report this key range using the index blocks to ZippyDB. And Zippy will report this key range to the primary. If it's the primary that's corrupted, it'll report it to itself. The primary will insert a patch request, which is this special kind of recovery request, into the Paxos log. Paxos will just automatically replicate this. And at some later time, every other node will actually encounter this patch request in its log. And if the corrupted node encounters this patch request, it simply waits around for the other nodes to send it a patch. And if it's not the corrupted node, then all the other nodes will try to assemble a patch and send it to the corrupted requesting node. Once the corrupted node receives this patch, it'll apply it and continue on its merry way with compaction. And this eliminates the corrupted data from the final compacted file. OK, so some evaluation numbers. What we really want to evaluate in this section is, one, this is a whole discussion about higher error rates. So really, how much higher of an error rate can ZippyDB tolerate with direct? And two, because we observe that we now actually recover only a very small key range as opposed to an entire data node, how much faster is recovery with direct in ZippyDB? So for our experimental setup, we got 60 Facebook servers, and we duplicated traffic from live servers to our testbed setup. And we injected errors on the fly in RocksDB with a special environment. So let's first look at error rate tolerance. So each of these graphs represents a particular Uber or bit error rate that we're simulating that is coming off of a drive. So in the upper left corner, you basically have the highest Uber, and in the lower right, you have the lowest Uber. So the red line in this case is unmodified ZippyDB, and the blue line is ZippyDB retrofitted with direct. So as you can see, the red line is all over the place in terms of read errors per second. And this is application read errors per second. And this is because as soon as it encounters a corruption error, the entire ZippyDB node will fail and try to come up somewhere else. And so during this recovery period, there's a high number of errors. And so it's basically really hard to tell if there are any errors at all with ZippyDB direct. And in fact, if I put this in a table form, you can see that the read error rates with direct are about 2 orders of magnitude lower. OK, and then another interesting thing is we wanted to determine if the size of this key range is actually large at all. So what we do is we plot a CDF of how many keys are actually required to recover a compaction error. So this is basically an estimate of how large these key ranges are per corrupted data block. And as we see, the higher the Uber, so purple is the highest Uber in this case, the higher the Uber, the larger the number of keys we have to repair, because actually each patch request will basically batch all the corrupted data blocks that it encounters during a compaction. So if you have a higher error rate, you'll encounter more data blocks that are corrupted during your compaction phase. And this is why when you have a higher Uber, you have more keys that you have to recover. And this actually directly translates into the recovery latency. So as we see, purple is the highest Uber, and it has the longest recovery latency, and red is the lowest Uber, and so at the lowest error rate, we have a lower recovery latency simply because we're recovering fewer keys. And so you'll note that the recovery latency is in milliseconds here. I didn't show you ZippyDB, unmodified ZippyDB recovery, but it takes on the order of minutes, almost like 30 minutes, potentially, depending on how much data sits in the ZippyDB server. And it's simply because it's using this very silly strawman approach to recovering compaction errors. So, in conclusion, we observe in this paper that we can actually just use existing distributed redundancy to fix hardware corruption errors. And the two main ways that we do this is we inspect the specific file layout for a storage application, and we also leverage the coordination layer of the distributed application in order to get safety. And by doing so, we can retrofit software to withstand these corruption errors and allow devices to expose higher error rates, which will allow them to have higher lifetimes. So, any questions?
Abhinav Del. So the key range that you're replicating, I'm assuming you're sending key value pairs in that case. Do you really do a diff, or you send the entire key range?
Yeah, no, you have to do a diff, because there's also in Rocks, you have to account for tombstones as well. So for example, there's like a special case where basically if the patch that's sent over doesn't have a key that you would have expected to be in the RAIN, you have to like write a physical tombstone in order to record that that thing has been actually deleted.
Okay, thank you.
Yeah.
Hi, Sam, no, Eunice. I don't get where the flash error, isn't this applicable to any kind of errors? Why is it limited to flash errors?
Yeah, this is generally applicable to any error, but I guess the point is people assume that errors are rare, and so error handling is actually not that great in software, I guess, for this reason. And I mean, a lot of works have basically shown, you could have some random file system error, right, and that'll cause your software to crash. But we approach this more from the perspective of we want to actually make hardware expose an error rate that will be visible and will actually directly affect software, and what would you do to change your software to handle that? Yeah.
Okay, let's thank the speaker.